So this is the big O complexity chart, which shows the most common time complexities. And in this video, I'm going to show you the difference between these time complexities. We're actually going to test the execution of these code examples in a way that we can chart it on a graph similar to this big O chart. We're going to use real data. I'm going to plot it on Google Sheets so you can turn your theoretical knowledge of time complexity into practical insights that translate into real code. So we're going to start with constant, logarithmic, linear. We're actually going to skip linear rhythmic, which is just a combination of linear and logarithmic. I want you to more kind of understand intuitively the building blocks that'll allow you to figure out other time complexities on your own. And then we're going to look at quadratic, exponential, and factorial. This video does assume some very basic knowledge of algorithms and time complexity, but as a quick recap, let's get clear on some definitions. What are algorithms and what is time complexity? Algorithms is just a sequence of step-by-step instructions. So all programming code is basically an algorithm. The most simple, common, and concrete example of an algorithm is a simple function. A function takes in some kind of input and gives some kind of output. The transformation of the input into the output is the algorithm. So here's a very quick example of that. We have a very simple function that takes in two inputs, A and B, and returns the sum of those inputs. So in this example, when we use this function, the number 1 and the number 2 are our inputs. And then the algorithm is when we return A plus B in the definition of the function. And then the output's whatever is returned from that function, which is saved into this output variable. So just to confirm, if I print the output, and I run the code, I get 3 because we printed the output variable which contains the output. So the algorithm is simply what transforms the input into the output. Now, time complexity is the speed efficiency of that algorithm in relation to the input. So if we look at this big O chart, the x-axis is supposed to represent the size of the input, and the y-axis is supposed to represent the time efficiency of that algorithm. So it says elements, which can represent the size of an input. So if we have an array of elements, then the more elements means the size of our input is bigger. And then operations is the number of operations that the code has to execute, which translates into the speed of the code. The more operations the code has to execute, the slower it is. The less operations it has to execute, the faster it is. So we can see log n, or a O of 1 time complexity. Basically, that means as the size of the input increases, the speed of the algorithm doesn't increase much more. It stays pretty constant. On the flip side, if we look at an algorithm with a factorial time complexity, as the size of the input increases, the speed of the algorithm very quickly slows down and becomes very inefficient. Now let's go over some simple examples for each of these time complexities. You should understand these examples as a first step in understanding how to analyze the time complexity of an algorithm. All right, so let's start with the constant time complexity. Here's a simple algorithm that has a constant time complexity because no matter how big n gets, this algorithm is always going to run at the same speed. Instead of us just theoretically declaring that this algorithm is constant speed, let's run this test. So basically the way this code works is I have some input sizes that we're going to test this algorithm on, starting from 1 all the way up to this very large number. And we're going to iterate through all those input sizes. And then for each input size, we'll print out the value. And then after we print the input value, we're going to get a start time. Then we're going to run the algorithm. Then we're going to get an end time. And then we're going to get the execution time in milliseconds by doing end time minus start time times 1,000. And we're just going to print the execution time. So let me run that code. So we can see input size starts at 1. It's about 0.008 milliseconds. It goes down to 0.002 milliseconds. So it kind of stays at 0.002 milliseconds no matter how big the input gets. And so if we actually plot this on Google Sheets, what it's going to look like is it's going to give us this chart where the x-axis is the input size and the y-axis is the execution time. As you can see, there was an initial spike in execution time, but overall, as the size of the input increases, the execution time stays constant. No matter how big the input gets, the execution time does not increase at all. Here's another practical example of what a constant time complexity might look like. We have an algorithm that just returns whether a number is divisible by 2 or not, which tells us if the number is even. This algorithm is also constant because no matter how big the number gets, it's always going to just do one operation to compute whether the number is even or odd. So now let's look at the logarithmic time complexity. So this is an example of a logarithmic algorithm. The number of operations this algorithm has to execute only increases by 1 for each time the size of n doubles. So you can see in this algorithm, we loop until the log n variable is greater than or equal to n, and then we return log n. So you can see in this algorithm, we have an example variable and a log n variable. The log n variable keeps track of how many iterations we've done in this while loop, and the example variable is going to double in size for each iteration in the while loop. So to demonstrate that, if I have this algorithm in here, and if I print the output of the logarithmic function, function starting with 1, and then each time I will print the output of the logarithmic function with an input size that is doubled from what it was before. If I do that, as you can see, it starts at 0 and then it goes 1, 2, 3, 4, 5, 6, 7, 8, even though the size of the input is doubling, and that's because we're returning log n, which only increments by 1, so it keeps track of how many operations we've done relative to the input size. It only does 1 extra operation for each time the input size doubles. So it's a very efficient algorithm. You can get to a size that is over 2 billion, and the algorithm is still going to only do around like 32 steps. So let's run this test. This is similar to the previous one, except this is going to be for the logarithmic function. Okay, that was very fast. We can see we start at input size 1. It starts at 0.001 milliseconds. And as the size of the input doubles, it gets a little slower. It gets up to 0.003 milliseconds, but it doesn't increase that much. So if we plot this on Google Sheets, we can see as the input size starts to increase, the algorithm gets slower and slower, but then it flattens out because remember, there's only 1 extra operation that is done for each time the input size doubles. So when it's small, it doubles many times. But then as it gets bigger in this graph, because this graph is a linear representation of the input size and the execution time. It doubles many times over here, but then it's only going to double once in the middle, once in the quarter point, and then here, and then a bunch of times here. So we can see this curve, which is actually very similar to the Big O chart. Actually, you can't really see it, so I'm going to pull up another picture. So here I just Google searched logarithmic time complexity, and we can see the logarithm right here, which is, it's in red. See how it starts to go up faster, but then over time as the input size increases, the growth of the execution time gets slower and slower. This is showing something similar. There's a curve and it starts to flatten out, and that's exactly what we've shown with our Google Sheet plotting the data. So here's a practical example of a logarithmic function. This is a binary search function that tries to find an element in an array, and it does it by eliminating half of the operations for each iteration in the while loop. So since we're eliminating half of the possibilities, the number of operations that is done only increases by 1 for each time the size of the input doubles, which makes this algorithm have a logarithmic time complexity. Here's a linear algorithm, and the reason it's linear is because as the size of the input increases, the number of operations that we have to do increases proportional to that, because we're iterating through the full size of n. We're not eliminating half of the possibilities or anything like that. We're iterating through the full size. So it makes the time complexity linear. And so here's a test that we can run. And basically this is going to tell us the execution time for numbers that start at 1. And then for each consecutive test, we're going to double the size of the input. So let's see what it looks like running this code. So maybe you didn't notice, but it roughly was doubling each time as well. So if we plot that code on Google Sheets, what it's going to look like is it's going to look like this. So as the size of the input increases, the execution time is going to increase linearly. Notice how there is no curve because the speed of the algorithm is directly proportional to the actual input size. Now, if we run this code's going to print 10 because when we pass in 10 as an input, we're going to add 1 to the n variable 10 times as well. So we can see the number of operations again is proportional to the actual size of the input. That's why it's a linear algorithm. Here's a more practical example of a linear algorithm where we try to find the greatest element in an array, and we do that by iterating through the entire array and keeping track of the maximum number we've seen so far. So this is big O of n squared. We can also verbalize this as quadratic, and basically we're doing a linear operation like we did in the previous example, but we're doing that linear operation a linear amount of times. So we're doing n times n operations. So here's an example of a quadratic algorithm where we're doing a linear operation a linear amount of times because of the nested for loop. Basically, we're going to test the speed of this quadratic function by testing input sizes from 100 all the way up to 6,500 in increments of 100. So 100, 200, 300, 400, all the way to 6,500. So let's run this code. So as we can see, as the size of the input increases, the speed of the algorithm is getting slower and slower at an accelerated rate. And we'll actually plot it on a graph so we can show you that. Maybe it's not obvious seeing how slow the algorithm is running. But basically, I've already plotted this on a graph, and this is what it's going to look like. It's going to start curving up. And it gets slower at an increasingly slower rate as the input size grows, because in the beginning, when we're going from 1 to 2, we're only doing a couple more operations, but when we're going from 1,000,000 to 1,000,001, we're doing like 1,000,000 more operations because we have to iterate through the entire 1,000,000 operations an extra time. And then notice how when we run this code, the output of this function is going to be 100. And n squared is the same as n times n because we're doing this linear operation a linear amount of times. And so 10 squared is 100, which shows why the time complexity is n squared. Here's a more practical example of an algorithm that is n squared as well. It is unoptimized. It can be made more optimal, but this is an example where we try to count the number of pairs in a list that is equal to a target when summed up. So remember here, since we have 2 nested for loops, this is why it's n squared. But if we have 3 nested for loops, it's going to be n to the 3rd power, or n cubed. This is equivalent to n times n times n. So 10 times 10 times 10 is in fact 1000. Each additional nested for loop we add in here that is iterating through the full size of n, it's going to increase the size of the exponent by 1. So if we add a 4th for loop which iterates through the full length of n and it's nested in the 3rd nested loop, then it'll make the time complexity n squared, or a quartic time complexity. And this pattern continues with each nested for loop that is added that iterates through the full length of n. All right, now let's talk about 2 to the power of n, or an exponential time complexity. Here's an example of an algorithm with an exponential time complexity. We can see here when the size of the input is 10, the output is 1024, which is actually 2 to the power of 10. So we can see 2 to the power of 10 is 1024, because in this case, 10 is representing the value of n because we pass in 10. And so it is 2 to the power of 10. Here's a test we'll run for this algorithm. We're actually only going to iterate through the number 1 to the number 26. We can't go much bigger than that because this algorithm is going to get very slow. So let's test this code. If I run it, we can see it gets to 23 pretty quickly, 24, 25, and then it starts really slowing down there at the end. We can see it looks like for each increase in the size of the input, the execution time actually doubles each time. So if we look to see how that's plotted on a graph, we can see that as the input size increases, we can see at the very end it starts getting very slow. And it gets slower much more aggressively than the quadratic or the n squared function, or the n squared time complexity. And if you think about it, this exponential time complexity is almost like a reversed logarithmic time complexity, because instead of the number of operations increasing by just 1 for each time the size of the input doubles, this is the opposite, where the number of operations doubles for each incremental increase in the input size. In order for you to understand why this algorithm has an exponential time complexity, you do need to understand recursion. So if you don't understand recursion, that's something you're going to need to do on your own. That's kind of outside of the scope of this video. But assuming you do understand recursion, I'll explain why this algorithm is exponential. So basically the way this algorithm works is, let's say we pass in 10 as the input. We're going to check if 10 is less than or equal to 0. If it is, we'll return 1. Otherwise, we're going to call the function again with the input 10 minus 1 twice. So it's going to be 9. And then 9 is going to come in. We're going to call it again 9 minus 1. It's going to go 8, 7, 6, 5. And it's going to do that all the way until we get to 0. And then when it's 0, it's just going to return 1. And so for each recursion call stack, we're actually splitting into 2 more call stacks. So if we call this algorithm with an input of 0, it's just going to hit this base case right away. 0 is in fact equal to 0. So it's just going to return 1. So it's going to have just one operation, one call stack. But if it's 1, what we're going to do is we're not going to hit this base case, and we're going to call the function twice again. We're going to go 1 minus 1 and 1 minus 1. So it's going to be 0, 0. So it's going to split into 2. And then it's finally going to hit that base case. So it's going to look like this, where it splits into 2. And then if we call with 2, it's going to split into 1, 1. And then for each of those 1, 1 call stacks, it's going to split into 2 again. So we can see each time we increase the size of n, we're actually doubling the amount of operations, because we can see from 0 to 1, we had to do these 2 operations again. And if we go from 1 to 2, we can see all these operations are happening twice, one here and one here. If we're going to call with 3, these operations are going to happen 2 times again. So each time we increase the size of the input, it's going to double in size, keeps growing. And so this is what it looks like as we increase the input size by just 1. Because again, each time we split into 2, for those individual call stacks, we then split into 2 again. So it splits into 2 recursively, which makes the time complexity exponential. So this time complexity is 2 to the n because we split into 2 call stacks each time we recurse. Now, if we were to split into 3 call stacks instead for each time we recurse, that would actually make the algorithm 3 to the power of n. And this exponential time complexity is going to represent how many times we split when we recurse in our recursive algorithm. So if I added a 4th recursive call, this would become 4 to the power of n. So we can see here when we call exponential, we're calling it with 10, and I set up this algorithm to where it's going to return 1 for each base case that we hit. And so if you think of the recursion call stack as a tree where we start with a big number, which is 10, we split into 9, and then 8, 8, 8, 8, and then 7, 7, 7, and then it keeps splitting up more and more down until we get to the 0. All the zeros, those are the leaves of the tree, or the very bottom of the recursion call tree. And there's actually going to be 59,049 of those call stacks at the very bottom. And it's actually going to be equal to 3 to the power of n. So I already tested this code, and this code does in fact print this number, which is equivalent to 3 to the power of 10. right? So now let me explain a more practical algorithm that is exponential. First, before we look at the algorithm, you need to understand what the Fibonacci series is. The Fibonacci series is a series of numbers where 0 and 1 make the start of the Fibonacci series, and then every number after that is going to be equal to the sum of the previous two numbers. So if we start at the end, 13 is equal to 8 plus 5, 8 is equal to 5 plus 3, 5 is equal to 3 plus 2, and so on. And that starts with these initial 0, 1 values. So here's an example of an exponential algorithm. This is calculating the nth Fibonacci number, meaning if we look at 13 here, it is 1, 2, 3, 4, 5, 6, 7, 8. It is the 8th Fibonacci number. So we passed an 8 into this number, it would return 13. And the way it works is it's going to sum the previous two Fibonacci numbers. So the 8th Fibonacci sequence is going to equal the 7th and the 6th Fibonacci. And we're going to add them together to get the current one. And the base case is if n is 0 or 1. And so we can just say if it is less than 1, less than or equal to 1, we'll just return n, which is 0 or 1. Otherwise, we're going to recurse and add the result of calling the Fibonacci function on n-1 plus n-2. Explaining this algorithm in more depth is kind of outside the scope of this video, but just wanted to show you a practical example. Now let's get into factorial, the worst time complexity. Now this one's a bit more rare, but if we look at it, if we pass in 10, we're gonna get 3,628,800 because I designed this algorithm to return the sum of the count of all the leaves of the recursion call stack tree, meaning if we remember how it splits up, we start with the big number and it splits up all the way down to the base case where n equals 1. Well, when it equals 1, we're going to return 1, and then we're going to sum all those ones up at the very top, and it's going to give us 3,620,800. And this is what it actually prints. And if we look at Google, 10 factorial is 3,628,800. So that clearly shows that this algorithm is n factorial. So let's run this code. We're going to have the factorial function, and then we're going to test the execution time of this function, iterating through the numbers 1 through 12. So let's run that. We already hit 1 through 10, and then we're still waiting for 11. So we can see it like 10x each time almost it looked like. And I'll kind of explain like how big it actually gets. We can see it went from 656 milliseconds to over 7,000 milliseconds or 7 seconds. So it got slow very fast. So here's what the time complexity of the algorithm looks visualized using real data. We can see it looks pretty choppy there at the end because we can only increase it by 1 and it already gets super slow. So it's not a smooth curve because from 10 to 11, it gets way slower so fast. And I'd have to wait for over a minute if we were going to test the size of 12. So if we look at this algorithm, we're not just recursing into 2 call stacks or just 3 call stacks like the exponential time complexity. For each call stack, this is actually going to make n recursive calls. So it's not a fixed number. The amount of recursive calls we make is dependent on the size of n. Imagine n was just 1. Well, then we're going to hit this base case n equals 1. It's going to return 1. It's going to be a single operation. But if n is 2, then we're going to iterate through the length of 2, and we're going to call the factorial function twice, and then it's going to hit that base case again. If the input's the size of 3, then we're going to recurse 3 times for that call stack. So 3 call stacks are then going to have 3 minus 1, which is 2. And then within those 3 call stacks, it's only going to do 2 iterations. And then after that, it's just going to be 1, and it's just going to return the base case. So I prepared this visual for you guys. And so basically when it's 1, it's just going to return the base case. When it's 2, it's going to split into 2 call stacks. And then in those call stacks that it splits into, it's just going to hit that base case because it's already 1. It's just going to return 1. And so this kind of visualizes the number of operations. And if it's 3, it's going to recurse into 3 call stacks. And then within those 3 call stacks, when n equals 2, it's just going to recurse into 2 call stacks. And then when we hit 1, it's just going to hit the base case, of course. When we hit 4, it's going to split into 4, and then 3 is going to split into 3 again. So we can see this is similar to the exponential, except as we go higher up the recursion call stack, it's going to have to split n times. So when we go from 1 to 2, it's going to do 2 times more operations. When we go from 2 to 3, it's going to do 3 times more operations. When we go from 3 to 4, it's going to do 4 times more operations. We can see this tree is happening 4 times now. When we go from 4 to 5, it's going to have to do 5 times more operations. We can see this tree is happening 5 times now. 1, 2, 3, 4, 5. When we go from 5 to 6, we can see that we're going to have to do 6 times more operations. This 5 tree is going to go 1, 2, 3, 4, 5, 6. So we can see that as we increase the size of n, the number of operations is multiplied by n as well. Instead of the number of operations doubling or tripling like an exponential time complexity, it increases by a factor of n. So the factorial of a number is actually all whole numbers from 1 to n. So the factorial of 3 is 1 times 2 times 3. The factorial of 10 is 1 times 2 times 3 times 4 times 5, all the way up to times 10. So that's the definition of a factorial of a number. So I just Google searched factorial of a number, and we can see that the factorial of 6 is 1 times 2 times 3 times 4 times 5. All the times 6 is going to equal 720. So basically, just to visualize it another way, the factorial of 4 is 1 times 2 times 3 times 4. And then when we increase the size of the input by just 1, we make it 5. The factorial of 5 is going to be equal to the factorial of 4 times 5, right? So we could just look at the factorial of n minus 1, and then we just multiply it by n, where n represents the input size. A more practical example of an algorithm that has a factorial time complexity is an algorithm that generates all permutations of an array. So for example, if the array has just one element in it, there's only one permutation, which is 1. For an array with 2 elements in it, the number of permutations are 1, 2, and 2, 1. And if we try and find all the permutations of an array with 1, 2, 3, it's going to look like this. Basically, you can see that these are all possible combinations of the array 1, 2, 3, where the order of them matters as well. And one key thing to note here is there is always a factorial amount of permutations you can make out of a list of items. So here's an example of an algorithm that returns a list of all possible permutations of the input list. Me explaining how exactly this algorithm works is out of the scope of this video, but that's what it does. To demonstrate that, we can run this code, which is basically going to run 6 tests for us. It's going to print the output of the commute function with the array with 1 element in it, all the way up to 5 elements in the array. So if we run this code, we can see when the size of the input is 1, it's going to give us this. If it's 2, it's going to give us this. If it's 3, it's going to be this. You can see it quickly starts to get very large if the input size is 4. And then when it's 5, it gets way larger, right? So let me actually output the format a little bit for us. So I just pasted the results of input sizes 1 through 4. We're going to leave 5 alone. It's a bit too big. But we can see from 1 to size 2, the size of the output doubles, where it's from 1 subarray to 2 subarrays. And from size 2 to size 3, the number of subarrays triples. And then from input size 3 to input size 4, the number of subarrays quadruples. And so that kind of goes in line with what we've talked about with factorial. And this also shows that, yes, there are a factorial amount of possible permutations of a list of items. So I hope this video has been helpful, helping you understand the most common time complexities. If you enjoyed learning about the different time complexities, then you are the perfect student that I would love to work with. I do have a one-on-one coaching program. Basically, I went from 0 to Microsoft software engineer within 12 months of teaching myself how to code. I didn't know how to code at all, and then within 12 months, I was working at Microsoft making $167,000 per year as a software engineer. Now I have a one-on-one coaching program. It teaches you how to code from scratch, learning all the necessary skills you need to become a valuable software engineer. I also give you professional experience that you can put in your resume. So if that sounds interesting to you, there's a link in the description of this video where you can book a call with me. And basically on this call, we'll figure out if we think we're a good fit to work together. This program does not end until you land the job. So it's full one-on-one coaching till you land the job, no time limit. If you enjoyed the video, please give it a like. And if you're an aspiring software engineer, I highly recommend you subscribe as well. I'll be posting more valuable content. Best of luck.